In this clip, I'm going to detail the mathematical expression for the volumetric flow rate, which is a double integral over a surface of the velocity field dot the unit normal vector pointing out of the control surface times a differential element of surface ds, this dot here representing an inner product. So let's assume that we have flow, so fluid flow, and we imagine a control surface inside of this, in the bulk of this fluid. Now this control surface, for now, I don't necessarily assume it to be a closed surface. So here I have just an open surface, and let me call this surface CS. Assume this is, for instance, seawater, and we're thinking about transport, and we're wondering how much salt flows through this particular surface per unit time. So how much sodium ions, for instance, flow through this surface at per unit time. So clearly two things will influence the flux of those sodium ion. First will be the concentration of sodium ion inside of the water. And the other thing which will influence this flux is the volume of water that passed this control surface per unit time. This is what is called the volumetric flow rate. Now this volumetric flow rate, or again volume of fluid passing through the surface CS per unit time, I will call Q. And from its definition, you directly see that the units of Q are units of volume per time. So those will be meters cubed per second. So how do we mathematically express this volumetric flow rate? Q. So let's go back to our initial picture. So we have to think about this surface, and through this surface there is fluid going. And so we have to look at every single differential element of surface which compose this control surface. So let me draw one here. So for instance, through every single element of surface, there will be a small piece of this surface called ds. There is some fluid coming through, and therefore there is a certain volume of water flowing through this ds. So if we want to compute the volumetric flow rate through the entire control surface, we have to look at the element, the small piece of volumetric flow rate flowing through ds. So let's write, so Q will be an integral, and Q will be equal to the double integral over the entire surface CS of dq, where I call dq the small volumetric flow rate through the small differential element of surface ds. Now again, dq will have units of meter cubed per second. So to find an expression for dq, instead of thinking about volume per unit time, we'll think about what volume of fluid passes through ds, not per unit time, but over a small time dt. So this quantity here will then be equal to dq, which is the volumetric flow rate per unit time, times the time that we're looking at, which is the small element dt. So what is dq times dt equal to? Now let's go back to our little drawing here. And let's zoom at our little element of surface ds. So here's my little element of surface. N here will be the unit vector normal to this piece of surface ds. And as you can see here, there is fluid passing through. And over the small surface ds, we can assume that the velocity field is relatively constant because ds is really small. And therefore, we can think of all of the fluid particle as moving at the same velocity, which will be u. Now, this velocity vector u here is the flow velocity vector at this particular point on the surface, so on this element of surface ds. And now the question is, how much volume of fluid went through this small surface ds during the time dt? So let me copy this and move it down here, just so that we have a good schematic. So this is our question. What is dq dt through ds? What is the mathematical formulation for this, expression for this? So to answer this question, we're gonna ask ourselves, where is all of the fluid that is going to pass through this surface ds in the next dt? So where is all of the fluid? So in which volume is the fluid which will in fact pass through ds over this time dt and will correspond to this dq dt here? Okay, so if we ask ourselves this question, then the first thing to think about are the fluid elements here, which are right underneath the surface. Well, in dt, they will have enough time to just pass through the surface. So the fluid which is right underneath the surface will be part of this volume. So we can start to draw a volume here of fluid in the same direction as u, because the fluid is moving in the u direction. So that fluid here underneath will pass through the surface ds over the next time dt. And the question is now, how far does this volume now extend underneath the surface ds? Well, because the fluid is moving at the flow velocity of u, the maximum distance it will travel over time dt is simply, so this distance L that it travels over dt is simply the norm of u times dt. This is the maximum distance L that a fluid particle here moving at velocity u can travel over dt, and therefore we know that the last particles that will be able to pass through the surface ds are at a distance L equals to u times dt. And so what you see from this reasoning is that the volume of fluid which is passing through ds over the small time t is actually this volume here, the volume of a prism which has a surface here ds and which extends a length u times dt in the direction of u. So the question is, what is the volume of this? What is this volume here? Now this volume here, actually I should have written it, corresponds to dq dt. Right? dq times dt is this volume here. So what is the value of this volume? Well, it will be ds, that's this surface, times this length, so times u, the norm of u, dt. And from formulas of the volumes of prism, you know that the volume of this prism here is equal to the surface times the height, and the height is taken in a direction normal to the surface of the prism, so in the direction n. But here there's a little angle, this angle between the normal n and u, and this volume is therefore ds times u dt times the cosine theta. U dt cosine theta is this length here projected on the direction normal to the surface ds. So if we rewrite this as u cosine theta times ds times dt, we get to our answer. U times cosine theta is the same thing as the velocity vector u dotted with the normal vector n. This is in fact the same thing as u dot n, and therefore this volume underneath the surface, which is the volume of fluid which will pass ds over the next dt, is equal to u dot n ds times dt, and therefore dq is equal to u dot n ds. So now that we have an expression for the small volumetric flow rate passing through ds, we can write the entire volumetric flow rate q through our control surface S, which is the double integral over our control surface S of u dot n ds. So this here is the volumetric flow rate through this control surface CS. So it's the volume of fluid passing through our control surface CS per unit time. And this quantity is very important because for every physical quantity which can be transported by mass transport, the volumetric flow rate comes into the formulation of the flux. So in our initial question, what is the flux of sodium ions, for instance? Well, that would simply be, through our control surface S, it will be the double integral of our throughout control surface S of the volumetric flow rate. So this is how much volume goes through the small element ds times the local concentration of sodium ion. If we're thinking about the mass flux, so phi, let me call this mass, and this becomes the double integral, of the control surface of the volumetric flow rate. So this is the volume passing through ds times the density. This is how much mass goes through ds. If we think about the flux of momentum, then the flux of the momentum will be the double integral over the control surface of u dot dn ds, which is how much volume of fluid passes through the small surface ds, times the momentum which is in this volume. And so now you see that indeed this part of the integral, this u dot n ds, does represent the volumetric flow rate through the surface.